so pleased to have Jason, a good friend of Encode, here to discuss Algorand smart contract language. And please do come on with questions and ask whatever you want. We've had such great interactive events, the last kind of 4 events previously, and I loved all the questions and the commentary. I know chat's been a fervent place, so please do continue that today. Do not be shy. Do post your messages anytime. You don't have to wait till the end. And Jason, again, thank you so much for your time, and also to Russ and Ryan as well. We're so pleased to have you guys back. And over to you to kind of tell us more about the Algorand smart contract language.
Thanks, Anthony. I appreciate it, and I want to thank everybody for taking their time to join this call. Today, we're going to be talking about one of the sophisticated features of Algorand, which is our Algorand smart contract language. So I'm going to talk a little bit about, from an agenda standpoint, I'm going to cover a couple things. I'm going to cover the types of smart contracts that you can do, and then how these can be used with additional features of Algorand to do additional things. And then I'm going to talk a little bit about the runtime architecture. How do these look when they're actually on chain? And then I'm also going to talk about the actual language that we use to write smart contracts. And finally, I'll wrap up with explaining some things that can make writing smart contracts a little bit simpler. Now, this is a fairly low-level talk, and it'll be fairly technical. So Russ is on the call. If you have questions, make sure you send them to Russ, and we'll give you a Discord link at the end to make sure that we'd like to have you join our Discord channel. So if you have questions on smart contracts, we got a fairly active community on Discord, and they'll be glad to answer your questions, and we monitor it every day. So with that, this is the agenda. This is what we're going to walk through. Hope that is what you've all joined expecting. So with that, I think I'll go ahead and just get started talking about what smart contracts are. Okay, for Algorand, we have what we have several layer 1 features. Like we have something called assets, which is what we're using to build NFTs or FTs with. And these are very simple things to do. It takes about two minutes to completely build out a NFT on Algorand or an FT, and very little code. We also have something called atomics, which allows you to group up the 16 transactions together. And if any one of these transactions fail, they all fail. So in order for if you group them atomically, they all have to succeed or they all fail. So those are some of our layer 1 features. And the reason I'm bringing those up because I'm going to discuss them with their use with smart contracts today as well. But our layer 1 smart contracts are fairly sophisticated in the way you build them and write the code for them, and then how you deploy them. And we're going to discuss all those angles. In addition, I will say that we do have what we call layer 2 smart contracts coming later, which are not considered layer 1 because they run out outside the chain. But in the context of this particular talk, we're just covering our layer 1 smart contracts. So what is a smart contract? Well, from our point of view, a smart contract is just a piece of logic, okay? And this logic is contained in a piece of code that's written in our what we call TEAL, which is our transaction execution approval language. Depending on how it's used, the same TEAL can be either what we call stateless or stateful. And I'm going to explain what the differences between these are, but by and large, for us, it's just a piece of logic. Depending on the type of environment you're in, you may have a few less or a few more different function calls that you can call within the smart contract. So we restrict some based on the type of smart contract that is. But the programming language is the same for all three, or for all the methods of deployment. So the first one we talk about is, okay, you can compile a smart contract and produce an Algorand account, like any other account on the system, whether it be a multi-sig, a single signature account, or what we call a logic sig account, or a contractor account. You can think of this as escrows. This is fairly similar to most blockchains, right? So you compile the logic, it produces an Algorand address. That's one way. Then you can transact from that account to another account on the Algorand system. That's, like I said, that's called a contract account. Or you can use escrow if you're familiar with that term. Okay, another way of doing it, using the same piece of logic, is to actually compile the logic, and then some individual signs that logic, and then that signed logic can then sign a transaction between two parties. We call that delegation. And I'm going to go into detail between both of these models in the slides to come to explain what the difference between those two are. But by and large, these are just used to sign transactions. You don't use them to do a contract account or an escrow. They're just used to approve or deny transactions. All this logic we're looking for it to do is return a true or false. That's what we're looking for. Okay, and then the final way is you can, well, by the way, we refer to those first two types as stateless. And the reason we call them stateless is because they don't live on the chain. You submit them at the time of a transaction that requires the logic. So you have to submit the logic as part of the transaction. And they're stateless because they have very limited access to on-chain data. They have access to anything in the transaction, some global properties, and that's about all you can get access to in a stateless contract. The other way of deploying it using an Algorand smart contract is actually deploy it to the chain where it lives. And when you do this, it's not like generating an account. When you deploy this logic in this fashion, we call it an application. And it's going to be the backbone behind any DApp you build on Algorand. So when you deploy that, you're going to get an application ID back. This is a unique ID to that particular smart contract. And then you can communicate with that particular app by making transactions to it. And we'll go through more detail on this. We refer to this one as stateful. And the reason we refer to this one as stateful because it has access to much more on-chain data. It can do things like get the last round time, what round number you're in, look up balances, look up asset balances, like what we talked about NFTs or FTs. If you create a unique one and someone opts into that asset, then you can actually read their balance and things like that. But in all three cases, the logic's pretty much looks almost identical. And you'll see that logic soon because I'm going to actually walk through debugging several examples to show you how I typically write applications on Algorand. All right, so moving forward, the first thing that we want to talk about is this escrow contract account, where we call this stateless. This is where we compile some piece of logic and it becomes an Algorand on an account on Algorand. Now, it will not be actually show up in Algorand's ledger until it actually gets funds into it. And these funds can take the form of being either algos, which is our native coin, or assets that you create, or any asset in the system, like we have USDC, that actually shows up in your ledger. So anybody can fund that account. There are no restrictions whatsoever on how the account is populated with funds, okay? But if any transaction wants to remove from the escrow to some other account, it has to be gated by the logic. In other words, if the logic fails, the funds will not leave the contract account. And so your piece of logic that you create and compile controls exiting out of the account, if you want to think about it that way, okay? And then the second way is, all right, we talked about what does it mean to be a delegate? Okay, so I have a piece of smart contract logic. What I do with that is I sign that logic with a standard account. So you sign it just like you would sign any transaction. So you're signing this logic, and with that, then later on, when you sign that logic, it produces what we call a logic signature. You can save this as a file, put it in memory, do whatever you want to do with it, and at a much later date, it can actually sign a transaction, and without the original signer having to sign again. So you sign a transaction with that logic, and that then gates the transaction. So if you want to think about this as what we typically use a delegate signature for, like this, is things like recurring payments. So let's say you have a power bill every month and you want to, you want the power company to submit the transaction on your behalf. Well, what you're doing is actually delegating signature authority by doing this. So you can say, okay, I want to let my power company take out 300 algos a month, no more, and only once a month. Well, you would write that into the logic, sign it with your private key, give that logic signature to the power company, who would then submit on your behalf once a month. And then the logic would be checked to make sure they're not withdrawing more than they're supposed to. That's what we mean by a delegate smart contract. And so those are the two types of what we refer to as stateless contracts. And generally, you can see the two types of use cases here where we say, for contract accounts, they're really good for escrows, hash time contracts, if you want to split payments between two beneficiaries, or if you want to do some type of limit order transaction on a trading site, contract accounts are great for that. If you want to do recurring payments or anything that you want to just give away a portion of your authority on your account, then delegated contracts work nicely. So those are the two types of stateless contracts that we got, and that's generally how that logic will be used. Okay, now let's talk a little bit about stateful. Technically, when I said there's just one piece of logic, it's what we call an application, a stateful contract. It's actually two programs. We have what we call the approval program and a clear program, and they both contain logic that looks fairly similar. The difference is when these are deployed, which program answers transactions, and that will really depend on the transaction type, and we'll go through that in the next slide. But by and large, these two programs are sitting out on the network, on the blockchain, waiting to be called by a transaction. And what they can do is they can write some global state associated with that particular contract. So let's say I'm counting votes for a political candidate. Well, the total votes may be stored in global state for each candidate, right? And then, in addition, it can write local state. So you can write in that same scenario, a local state. I might say, okay, this user opted into my smart contract and they voted on candidate A. Well, what I can put in the local state is who they voted on and did they vote or did they not vote. So you can actually store what accounts have voted and which have not. And so that's what we call local state, okay? So, and by the way, for global state, you can store up to 64 key value pairs. These are 64 byte values that can either be byte arrays or uint64s. And for local state, you can store up to 16 per account that's opted into the smart contract. Okay. One thing I'll also say is if you do not use any local state at all, no one has to ever opt into your smart contract to call it. And finally, the approval program is the main program that's going to be the one that processes most of the transactions. We have a clear program that can also modify both global and local state as well. And you'll see what the difference between those two programs are in the next slide. But we communicate with this with just a set of what we call application transactions. All right, and it's all it is you initiate what we call application transaction, and one of these two programs will fire and execute their code. So that's how you communicate with them. Well, this application type can actually can be further subdivided into basically 6 types of transactions, subtypes. So the first one we have is what we call a no-op, and it's a terrible name, but all it means is this is the generic call you'll be making to a stateful smart contract application. This is the one that'll get called when you create the smart contract or deploy it, when you make a generic call passing a set of arguments to it. And what it will do is it will trigger the approval program, okay? Then another option is to opt in. And the only time you need to use this transaction is if you're gonna modify local state for people. So that way you're not affecting their balance requirements associated with what how many algos they have to have in their account to actually opt into your smart contract. All right, so net, if it's no local state, you don't need this particular transaction, but it also triggers the approval program. A delete application, you can actually delete an application that you deploy. Now, you can also put code in there to prevent this from ever happening. So if you want, once deployed, never be able to delete, then you can actually put code in the logic to make sure that it doesn't do that. But it also triggers the approval program. Then we have an update application. So you can actually update the application. Again, as with the delete application, you can deny that capability if you want. And then we have the closeout transaction. This is, say someone's opted into your smart contract and then they just want to get out. This is a graceful way of exiting the smart contract. It tells the smart contract, hey, I want out of this contract. The contract calls the approval program. It can then clean up any storage that it's used for you and then let you out of the contract. But this call can actually fail. So if this call fails, you would think someone's stuck in that particular contract. Well, that's why we have the clear program. It's a non-graceful way of getting out of the smart contract. The logic still gets called in the clear program, and you can do whatever you want in global and local state, but this transaction is not allowed to fail. It will always return true. So these are the standard transactions that you'll see with application transactions. And just so you know, we have maker functions for all of these in all of our SDKs. So if you're using, and we have 4 SDKs, primary SDKs, there's a lot of community SDKs out there, but we have Go, JavaScript, Python, and Java. So those are the 4 languages, and there's like a Rust a Rust SDK out there. There's a Swift SDK. Yeah, you name it, where there's probably an SDK already out there. And all we use is REST API calls. So it's fairly simple to make an SDK for it. All right, so those are the 6 transaction types. Stateful, when would you use these? Well, if you're building an AMM, you're building a lending app, you're building a crowdfunding app, a voting app, anything that needs to track some type of global state and some per user state. And then you can do it for things like lotteries and material tracking, all kind of things. Right, so these are the typical use cases, and we like to think of these as they live on the chain. These are true live on the chain type applications. Okay, that said, there is some differences between the way these two can be used. They're actually evaluated at different times. The logic itself is evaluated at different times in the process of a round or a block on the blockchain. When you do a stateless contract, it's evaluated by the node you submit it to. And then on a stateful one is when it's pulling all the transactions together for final block assembly. You'll see this, you got size limits, which are fairly close. And then you have the opcodes. For every function you call in there, there's a cost associated with it. And right now we have a hard-coded limit for each one of those, and it's in here. I will say this is most likely going to change to a dynamic model. So take this one with a grain of salt for right now. And I'm only putting this slide in here so you're aware, and you can use this for reference later. But obviously Stateful has a lot more access to the ledger data, where stateless is only going to have the global variables and the transaction properties. And then and currently we have a set of templates for stateless, like HTLC templates, split templates, things like that. We don't have any for stateful now, but there are plenty of solution examples out on our developer.algorand.org that'll help you get started. So now that you know what the 2 types of smart contracts are, I want to talk a little bit about combining these with other technologies. And the best way to go about doing that is give you some real world example of some solutions that we built on the developer portal. So the first one I'm going to start with is a crowdfunding app. All right, and this is just the donation phase of the smart contract. There's other phases of the smart contract that you could implement slightly differently, but this is just that so you can get an idea of how these things can work together. All right, so first off, I have a stateful contract app that's basically my app. This is my app for the crowdfunding app. And when I got a set of global state values, like when does the fund start date, the end date, where you're trying to set some dates where you allow funds to be raised. You got a goal you're trying to achieve, and then the fund amount, which would be the current amount where you're at. And then we got a few other things that are used in the program for other things. We're not going to get into those details, but just those first couple ones should give you the idea of what we're doing here. But stateful smart contracts can't hold funds, not currently anyways. So I have to create a stateless contract to hold all those donations. So this is a stateless contract that's out there that's going to receive all the donations, but somehow or another, the stateful app needs to know that a donation was made and how much it was for. All right, so let's say I have a user who's ready to donate. The first thing they'll do is going to create one transaction to call the stateful contract app that says, hey, I want to fund this escrow, okay? And I want to fund this particular crowdfunding app that I want to stand behind. So they're going to say, okay, they're going to call the stateful smart contract, say, I want to fund that one. The second transaction they're going to make is, I got to make the payment transaction from the donor to the escrow account. So I have these 2 transactions. Well, that's not very helpful because I could do one without the other. And this can cause issues. So the way you get around that is you put logic in both contracts that say, hey, they cannot be called standalone. They have to be called in what we call an atomic group. So these are now, the logic will actually look to say, okay, there's 2 transactions in this group, and the first one's this transaction, and the second one is this transaction. And so anytime someone donates, I've combined this whole logic with just that atomic operation. And then the stateful smart contract can actually look at transaction 2 and go, oh, they gave this amount. So, and then they can increment the fund amount by that giving amount. And you keep the local storage there for the giver, because if the fund doesn't meet its goal, then you want to be able to give that money back to the original donor. So that's a concept of combining stateless, stateful, and atomic transactions. All right, so those are three, basic layer one features of Algorand. Let's do it. Let's walk through another example. So let's say we have a voting rule. Okay, I got a user that wants to vote, and so I create a stateful smart contract that has some similar type of thing, global variables, but mainly think about candidate A votes, candidate B votes. That's where an individual is going to vote for one of those two candidates. Okay, so the first thing that I want to do is the way I'm going to restrict it so multiple accounts can't vote is I'm going to create a voting commission where participants have to go get registered. They'll register with that commission. The commission will send them an Algorand asset or an NFT that says, or a FT that says this is a vote token. You can use this to cast your vote. All right, so the user receives that and they want to spend that vote token to make their vote call. So the first thing they have to do is create a transaction from the what we call an asset transfer from the voter back to the vote commission to spend that token. And the second thing is they want to call the stateful smart contract and say, I'm voting for candidate A or candidate B. Well, like we have the same issue where either one can be called standalone. Well, you can also prevent that with the stateful smart contract data. And you can verify that they have to be atomically grouped together. And so now the user can spend that vote token and cast their vote in the same operation. And the nice thing about this is if either one of these transactions fail, they both fail. So that's how you would craft and build smart contracts in different ways to create different applications on Algorand. And by the way, this is a fairly common way of building applications. Is often you're going to require that a stateful contract be wrapped atomically with some other call in the system. All right, so let's talk a little bit about the runtime architecture. The runtime architecture for the stateless kind of looks like this. I issue a transaction, one of the many types of transaction Algorand has. Let's assume a payment transaction. Well, as part of that, I have to pass the program itself and then a set of arguments that can be used in that TEAL program. That's the logic. Okay, so what that does is we have a stack engine that runs in the node. And what it's going to do is it's going to take your program and process one line at a time and have access to those arguments. So it can read some global variables, can look at all the transaction properties. And if you've grouped this with multiple transactions, you look at all the transactions in a group's properties. And then you got some temporary scratch space where you can store some things for the life of this one transaction. So this is the general runtime environment. So every time you want to use that logic, you got to write it. Now, it's not even, that TEAL logic is not even on the blockchain until you actually do your first transaction. And then it's on there, but you can't reuse that same logic. You can reuse it by submitting it again, but it's on there so anyone can verify that this particular logic was used with this transaction. Okay, so that's the stateless runtime architecture. And it's that stack, the little stack engine you saw in there kind of has this architecture we're going to show you here. Here's my program. Don't get caught up in the language of it yet. We'll get into that in a minute. But just assume this is our, it's in a similar like language, but we have your program on that gets loaded one line at a time onto the stack. And it's processed one line at a time. Well, each one of these lines has what we call an opcode. And this opcode operates on the stack. It either pops values off, pushes values on, or maybe just does one or the other, one or the other, not both. And in fact, it can actually pop multiple values off and only push one, or pop one value on and push two values on. So, but that's the stack engine. It can be up to 1000 B, and it supports uint64s and byte arrays. You got a set of arguments up to 255 arguments in a stateless architecture, where you can pass up that many arguments to the TEAL program, and you saw that in that slide before. And then here's some of the transaction properties you can get access to, like I can get who the sender is, the fee, the first and last valid, the note in the transaction, the amount of the transaction, those type of things. And then finally, I got a little scratch space up to 255 in the scratch space where I can store temporary values. So that's basically what the stack architecture looks like. And don't let this scare you, because wait till you get to where we're actually running code and I'll show you. It's not that difficult. Okay, stateful is a little bit differently because the logic lives on the chain. You don't have to provide it. All you do is make an application transaction. And every application transaction allows you to pass a couple of arrays. One, you have the arguments array, much like the previous one. But in addition, we have something called an application array, accounts array, and an assets array. These are very important to understand when calling stateful apps. In order to make smart contracts very fast on Algorand, we limit smart contracts access to the ledger. They can't read the entire ledger. They can only read the ledger for certain values that are passed in. So for example, when I look at application array, that means I want to go read another smart contract's global values. So if you have, let's say, 2 smart contracts that are linked and I want to go read its global values, and I have to pass its application ID in an array to the transaction. Now, another thing too is I can go look up the ledger balance for anything for the user who is sending the transaction. But in addition, I can read and write his or hers local storage. If I want to do other accounts, which is often required in stateful smart contracts app, I have to pass those additional accounts in an accounts array. And this is just their account address, an array of their addresses. And I can pass up to 4 of those. So in total, I can modify 5 different accounts in one transaction. And then finally, we have this assets array. And the only reason you ever need this is if you're trying to get the configuration for an asset, like you want to know its unit name or something like that. If I want to know how many, let's say I create the Russ coin and I put it out on our testnet, and I use an account to opt into that. If I put my account in that accounts array, I can read my Russ token balance. But if I want to know how the Russ token was configured, I would use the assets array. And this is very important to understand when you're going through TEAL code, that you have these 3 arrays that are passed in addition to the arguments. Okay, so they live now. The TEAL program lives on the node and on the blockchain itself. So the stack's very much the same. It can read global variables and transaction properties. But in addition, it has a temporary scratch as well, but it has global and local state. That's the big key differentiator. In addition, some of the opcodes that you'll see in the programs, you have a little bit more access to additional opcodes. And I'll show you how to tell the difference between what opcodes can be used where as we get further into the talk. All right, so similar, this looks almost identical to the stateless architecture with the addition that you can have up to 4 accounts, two applications, and 2 assets. And obviously, and the number of arguments are a little bit different. You can pass up to 16 arguments and no greater than 2K worth of data and arguments. And then finally, you have the global and local state, which is 64 key value pairs on global, 16 on local. All right, so that is the 2 runtime architectures. Let's talk a little bit about TEAL. Okay, TEAL is, like I said, is a bytecode based stack language where it just returns true or false. Generally, this is determined by whatever's left on the stack at the end of all your program execution. If you've left 1 positive value on the stack, it'll return true. Anything else will return false. Now, there are a couple opcodes that'll only take the last value in return. So that's not a 100% true story as far as having it. So typically, if you don't put one of those opcodes in there, if you have a 2 positive values left on the stack, then the program would fail. But in addition, we have full SDK support to interact with smart contracts. There's over 80 opcodes that you can call. You got to have access to things like ASA balances, algo balances. You can read all transactions in a group, and obviously with Stateful, you have global and local storage. And I will tell you, as a precursor to something we're going to cover later, while the language may look a little bit daunting, at the end of the day, you can always write these in Python using a tool called PyTeal. But there's even another option on top of that we'll discuss as we get further into the talk. All right, so first thing, let's talk about the simple stack example using some opcodes from Algorand's opcode spec. All right, so we have this piece of code. It's only 3 lines. Now, all it tells, what it's really trying to say is, I want to know if the transaction amount is greater than 1,000 microalgos. So we use this, what we call TXN opcode, and then the property that we're interested in getting. In this case, we're looking for the transaction amount. All right, so what happens is that first line reads the transactions amount pushes that onto the top of the stack. And then it processes the second line. Int 1000, int's a pseudo operator that just loads that integer on top of the stack. So now it pushes the transaction amount down the stack and pushes the 1,000 on top of the stack. Okay, and then the final operator is the greater than or equal to. What it does is it actually pops 2 values off the stack and pushes one value on the stack. And the value it pushes on the stack is 0 or 1, depending on if the first argument is greater than or equal to the second argument. So that's the basic operation behind the way the entire program works. Okay, the whole stack engine works. The opcode definition will look something like this. This is the greater than and equal to. Okay, it pops A and B off the stack and pushes a uint 64. And then it says A greater than or equal to B, and we're going to push a 0 or 1. So that's the opcode definition. Okay, well, I told you earlier that in some cases you'll use stateless contracts, some cases you'll use stateful contracts. There's a tag in the opcode reference manual that says either mode application or mode signature on some calls. If it doesn't have it, it can be used in both. If it says mode application, it can only be used in stateful applications. If it says mode signature, it can only be used in stateless contracts. And let me show you the reference. This is the opcode reference. Every call that we got is laid out in the same fashion. And it's on our reference documentation, smart contracts, opcodes on our developer site. So you can look through every one of these. So let's go back. Okay, so we were talking about a couple things. These are some of the pseudo operators to load data onto the chain, onto the stack. You can see where we have already covered the int one, where we loaded that 1000 onto the stack. And then we have byte, which loads a string. So you can see I'm loading my string onto the stack and seeing if that's equal to the first application argument, to that first transaction argument. And then finally, we got ADDR, which converts that to a byte array, an Algorand address to a byte array. So in this case, I'm just trying to check and see if the receiver of the transactions, this is their address. That's all I'm checking. All right, so instead of keep digging in this, let me just show a quick example. I think that probably hopefully this will clear things up a little bit. But let's say I have this, I got my development environment set up a certain way. This is VS Code, and I have what we call a private network. And all it is a couple shell scripts that call our goal command line tool. And so if you look, I got this start net, which basically just, where's it at? Okay, where's my goal command? Oh, right here. All right, so right here where I'm doing a network start, and then it's using this template that I've defined right here. And this template just says what state goes where, how many accounts are in the system, that kind of thing. And so I can start net and I can stop net. I wrote these just to be able to start the network pretty quick. And then I got that window open up here so I can stop and start a network pretty quick. And then in my directory here, if I go back to that create state one, let me make sure I'm in the right directory. Okay, so right here, create state right here. Okay, so in this particular case, all I'm doing is creating a smart contract here. This is my application ID that is just going to return. This is just a link to my goal command. So here I'm doing goal app create, and I'm passing in some arguments. Like first argument's 10, passing in the creator account. Then I'm passing in the approval program, which is called global TEAL. And this is the number of byte slices. In global state, you can either have byte slices or integers in both global or local state. So you have to specify when you create it how much memory state you plan on using. And this is so because anytime state's used in a contract, minimum balances requirements go up. So that's one reason why this check is needed. So you're specifying how much state you're going to use in these 4 values. And then finally, I'm passing the clear program. That's all this does. And that creates it, launches the stateful smart contract out onto the web. All right, so if I run this, give me 1 second. Okay, first thing I want to do is start the network. Okay, you see it starting up me a private network, and then I'm going to try this again. All right, so it's creating my application and deploying it on my test net, on my, not test net, on my private network. All right, so it's deployed. Now to call it, I'm gonna actually debug it because we have this debug application. Is the best way to learn TEAL is to actually debug it and walk through it. So here, I'm gonna make a call to that application. This is its ID. Now the reason I've hard-coded 1 is because I'm restarting the network every time. So I know it's gonna be the first app created. I'm passing some arguments and I'm saying what counts. So instead of actually submitting it, I'm dumping the transaction out to a file, and I'm using our what we call our TEAL debug utility to debug it. And I'll show you how that works. So let's debug state. All right, so now if I go over here, I'm going to go to Chrome and I'm going to just type in Chrome inspect. And this is actually setting up a remote connection for the Chrome debugger, is all that TEAL debug tool does. So, so when I do that, I can now debug line by line my Stateful Smart Contract app. So here's that stack that I referred to many times. Here's my transaction that I submitted. And if I had a group of transactions, they would all show up in here. And then here's my global state. Right now, I only got one global state variable and it's named, the key value is called counter and its value is 1. All right, but let's stick with the stack because that's the most important thing to watch when you're running your program. All right, so the first thing is just the Pragma version 3 just tells you what version of TEAL we're using. So I'm going to use the pseudo operator called byte counter, load the word counter onto the stack, and then I'm going to use this, what we call, this is an opcode called app global get that actually goes and reads that value for this particular contract. And it reads it and it says, okay, the value is 1. I'm going to add, push another 1 on the stack, and I'm going to use the plus operator to add those 2 together. Now we got 2 sitting in the stack. Then finally, I'm going to store that in one of my scratch spaces. So I store it, so it pops it off the stack, and now it's in my scratch space. Then I'm going to load up the same key value name called counter, and I'm going to load the value that I want to set it to, which will be 2, that I'd stored in the scratch space. Then I'm going to use app global put. That's how you write a value back to global state. And so I put that there. All right, now that clears my stack. If I were to return right now, the program would fail. So I load the value back up just so I can return with a positive value left on top of the stack. And that is all there is to calling a stateful smart contract. There's you can do a lot of complex logic, but that's the fairly simple view of the way that calling a stateful smart contract works. So, oh, one other thing too, you know, let me show you one other thing. Now, TEAL is not a Turing complete language, meaning you cannot do loops. Now that's very likely to change in the next, in a very brief amount of time. But currently we do have branching. We have 3 opcodes for branching. One's called B, one's called B and Z, and the other one's BZ. B just means you can branch forward, and if you use that opcode, it'll immediately branch to a label you got in the future of the program. If you use B and Z, that's a conditional branch. It says, okay, if the last value on the stack is positive, then I want to bounce to the new to the label. If you got BZ, it says, oh, if the last value on the stack is a 0, then I want to branch. So we cover all 3 cases for branching forward. Let me show you a quick demo of the way that looks. So you're gonna have to watch me stop and start the network. I'm gonna do this a couple times just because it makes it nice and easy to debug, make sure I'm not doing anything else that may mess up my code. All right, so here, and then I'm gonna go ahead and create branch. Okay, and this is deploying another stateful smart contract. Won't go into the details of it. You'll see the code in a second. Now I'm gonna debug that same way I did the first one. Okay, same thing, you get the connection. So I'll go back, come on, go away. All right, I'll just do it this way. So you can see this. All right, see there, I can hit the inspect button. All right, and here's my program for the branch. So what I'm gonna do is I'm expecting 2 application arguments to this particular transaction. So this is a transaction property, non-map R's. How many transaction properties were there? So I read that and it says there's 2. Well, then I'm loading in it 2 because I'm expecting there to be 2. And then I do an equal, which pops those and writes a 1 or 0, depending on if they're equal. Now, the BZ finished, if they were not equal at this point, BZ finished would bounce down to this line 21 and return a positive value. So it'd say, okay, it's okay to call this would something other than two application args, but I'm not going to execute the rest of the logic. I'll just return a true. All right, so we move along. I'm going to put the word my arg onto the stack, and then I'm going to read the first transaction argument, and it happens to be named my arg. So I'm comparing those two, and if it's now I'm doing a B and Z. So this will, since it is true, since there's a 1 left on the top of the stack, it will go to this check second arg. So you see it bounce down to this label from line 13, and now I'm going to read the second argument here. And then this brings in basically a byte, a set of bytes. I'm going to convert that to an integer. And that says, okay, that's 1025. Now I want to load 100 on the stack, and I want to know if 1025 is greater than 100. And it is, so I'm B and Z in to finish here because there's 1 left on the top of the stack. Had that failed, then we would return the failure of the smart contract at that point. So that's the idea behind branching. Okay, so moving along. All right,
Jason, we have 2 questions. I don't know when you want to do that. Want to do that at the end or just interject?
Yeah, I'd rather if we can wait till the end, that'd be best for us.
All right, I will. Thank you.
Okay. All right. So like I said, we can access transaction properties. You already saw that where we're just loading transaction amount and then loading int 1000 and doing a greater than or equal to. That's what the program would basically look like. These are not all the properties, but these are most of the properties that you can access. Okay. The opcode documentation will show you exactly which ones you have access to. In addition, we have a set of global variables. Now, depending on whether you're stateless or stateful, the global variables may or may not be available. Like, for example, here we have latest timestamp. That is only available in a stateful smart contract. And then you got like group size that says, okay, we're doing an atomic operation. How many transactions are in the group? And then we have something called zero address. What this does is allow you to do the negative test of did someone set a particular address in a transaction. So we have this feature called close amount to. That's typically when you want to close out an account and give all the funds to some other account. Well, if that is set to zero address, that means that this is not a closing amount to transaction. So you always want to do tests to make sure everything you're expecting is set correctly. And this prevents some, because that particular function, that particular transaction type can actually close out an account. And if you don't code for it, then you're going to end up losing funds. All right, so those are some of the global variables. And then you can also check the transaction type. All right, so we have basically 6 known application types in Algorand. We have payment types for doing general payments with algos. We got key registration for participation and consensus. We got asset config for configuring an NFT or FT. We have asset transfer. Well, I want to transfer that newly created asset. And then there's another option. Assets can be frozen and they can also be clawed back, by the way. But you can also disable both those behaviors as well. So we have an asset freeze transaction. Then finally, we have an application call. Well, you just use the type enum property and you can read the actual type using the constant name and int the constant name, and that'll do the correct integer conversion for you. In addition, for the application types, which was the one we're covering today, we have 6 additional ones that we discussed earlier in the call, which were no op, opt-in, closeout, clear state, update application, delete application. You can actually check the transaction subtype using the onCompletion property. So you can say, okay, if it's no op, this is what I'm doing this operation right here. All right, so this is where you would, if you didn't want somebody to be able to update or delete, if they called one of those, you would just return a failure. Put an int 0 on the stack and then hit return. Or put there's an opcode called assert, which would fail immediately and then reject the transaction. Okay, now let's talk a little bit about atomics. You've been seeing this word TXN everywhere. Now let's talk about GTXN. GTXN allows me to specify which transaction in a group. So in this particular case, the only difference is I have to add an index after the TXN word. So in this case, first thing I'm checking is getting the group size, saying, okay, is there 3 transactions in this group? Okay, there are. Let's move on to the next condition. I'm checking when I say GTXN 0, that means give me the first transaction in a group, and I want its type enum that we covered just a couple slides ago. So saying, okay, is this type application? And if it is, I'm ANDing those 2 sets of conditions together. I'm checking the second transaction to see if it's a payment transaction and that condition together. And then the third transaction, is it an asset transfer? Man, and those three conditions together. So at the end, this is a complete program, because at the end, it's either going to have a 1 or a 0 on the stack, and it'll return a success or failure. So now, you obviously, these are just examples. You should have a lot more code in there for safety reasons, but for teaching, for this teaching scenario, I think it makes it easier just to see the simplified version. So that's an atomic version. I think I can show you a quick example of that too. Okay. So let me stop and start. Okay. And create the atomic. All right, so I'm creating this atomic, and it just deployed. The atomic one is just deploying the application first, but then I'm going to debug this atomic. Now, this is a little bit different because I'm actually doing 2 transactions in Go. These are all, by the way, anything you see me doing in Go can be done with the SDKs as well. All right, so I'm making 2 transactions. One's an application call and one's a payment transaction. Okay, so what I'm trying to do is then all this does is group them. This is how you do an atomic when you're using the command line. It's a little bit more difficult to do it from the command line than the SDK. SDK is fairly simple to do this, but this is me still running the TEAL debugger down here on a group transaction. And by the way, all these examples are available in the link I'll share at the end. So let me debug that atomic. All right, so now it's creating the transactions, grouping them, splitting them up, signing them, and now it lets me go into my debugger. Okay, so I'm gonna inspect that, and you can see here's my program. This is the only difference is between this and what you saw on the slide was I'm only checking 2 transactions as opposed to 3. So if you look, here's my 2 transactions. I'm looking at the stack. I can then walk through. Okay, here's one other thing this is a new one that I didn't say anything about yet. The transaction application ID, that is the ID that the system assigns your stateful smart contract when you deploy it. If you check it in code to say, is it 0, that means this is the first time your approval program is ran and you're actually creating the smart contract at this point. So you'll see if that's true, I B and Z to creation and just return. Because I don't want any logic to execute while it's in creating the smart contract. I want it to execute when we call it and normal calls. So in this case, it's already been created. I'm debugging it now. So it's not creation, so it's not going to jump to that. Now it's going to check the number of transactions. Okay, it says there's 2 in this group. I want to make sure of that, and then I'm going to check both types. First one's a application transaction, ANDs those together. Second one's a payment transaction, going to AND those 2 together. Then I'm going to check the amount. I want to make sure the amount is at least 10,000 micro algos. Technically greater than 10,000 micro algos. And the transaction is actually for 50,000 micro algos, which is going to be successful. And those 2 conditions. And now I can just return because I'm left with a 1 on the stack. And that's pretty much all there is to that. All right, so going back. All right, another thing you can do is like do asset checks. Remember when I told you we had this accounts array? Well, there's an index. If some calls use an index into those arrays. For example, when I want to check it's your asset balance, like say that Russ coin we talked about, I can call this asset holding get and then specify I want the asset balance. That pops 2 values off the stack and returns 1 value, 2 values. The 2 values that pops off the stack, the first one is the index into the accounts array. Int 0 means the sender of a transaction. Int 1 means the first account, added account. Int 2 means the second added account. So this is an index into that array. And then int 2 is this, in this case, is the asset ID. Just like stateful smart contracts get an ID, assets get an ID. And then I'm calling get balance here. It's going to return, first off, did it find that was the call successful? And the second one would be the actual balance. So in this case, I'm just popping the value, whether it found it or not, popping that off the stack and then comparing the remaining value to see if it's greater than or equal to 1. What this is telling me is, does this person have any balance in this asset? That's all this TEAL code's telling me. Okay, then we also have the concept of reading other smart contracts. You pass those in the application array. So that's just an index of app IDs, and then I can actually go out and read those. I'm not going to run that demo right now. Okay, so another thing we can do is, like I said, well, you can read and write state for individual users. This is only required for when writing local state, or is if the user, you're only allowed to write local state for users that are opted into your smart contract. You can actually have code decide, oh, if this is this account, I want this account opted in. I'm going to write to their state and jump that code if the user hasn't opted in. So it allows your stateful smart contract to be called at any time, but not necessarily write to local state. But if you do, this the way you would do it is index into that array. So in this case, I'm saying the sender because it's int 0. This is the key value. This is the value I want to set it to, and then I'm storing it using app local put. Same with reading it back up. You pass the index and then the key you're interested in and call app global get. I can also do for other accounts like this. If I want to get the first account in the accounts array, I just say int1, and then I specify the contract that I want to read their value of. So it may be an entirely different contract than the key that I'm interested in reading, then app global get ex. And one thing to note is for any of the users, the sender or the 4 users, not account array, you can read and write up to those 16 pairs of local state. In addition, you have read-only access to any stateful smart contract in the network's local state for those 5 users. So that really, it makes it a nice way to be able to go out and read another smart contract's local state for account 1. Okay, and then finally, I am going to show an escrow demo real quick because we haven't really covered those, but I got an escrow here, right here. When you compile that, this logic called escrow.teal, it produces this address. So the first thing I'm doing a payment transaction to fund that address, then I'm going to send from that escrow to another account. So this is where that from program comes. Instead of signing it with an address, private key, I'm signing it with the logic. All right, so if I just go debug escrow, shell. All right, so it creates the first payment transaction to fund the escrow because it hasn't been funded. And then the second transaction is the payment out of the escrow. So if I inspect that, you can see here, this is my stateless smart contract code. So I'm checking that, I'm verifying that this receiver, transaction 0, is this address, hard coded, right? So first thing I got my bytes for the receiver, and I'm getting the bytes for the address that I want, and I'm comparing to make sure they're equal. And then I'm doing a few other checks like on fee. And this final stuff here, remember what I told you about rekeying? We got close remainder 2, asset close 2. It's very important that you check these type of values to make sure someone's not closing out of your account, your escrow, to kind of swindle the money out. And so these are just a bunch of checks are all ended together. And the final thing is always know what you're expecting in the code. If this is group size is more than 1, then somebody may be trying to tail a second transaction onto something and make some type of hack. So always check things like your group size. Make sure test the things that you're expecting, and then these are all ANDed together, and finally just returns with that 1. The program runs out. So that's simply doing an escrow, and same kind of concept for debugging it. Okay, let's talk about simplifying this. I've covered a lot of different opcodes and some of the ways that you can debug and work with smart contracts. So let's talk about simplifying it. So I have this TEAL here, and some of you may think it's too complicated. Some may not. I will tell you this: if you go through the debugger a couple times, it really starts to simplify things and make it somewhat easy, in my opinion. But regardless, if you don't want to use the TEAL code by hand, you can always write them in Python and using our PyTeal compiler, and it'll compile to TEAL. Okay, another option is to use what we call Reach. Reach is a framework that outputs smart contracts for both Ethereum and Algorand. And what it does is it allows you to only worry about the business logic of an application. It's a JS-like language that you're writing the actual contract stuff with. And you can, the UI interface, you can write many different languages, but the logic associated is kind of like a JavaScript-like language. And what it'll produce the TEAL code for you. Not only will it produce the TEAL code for you, it will formally verify that TEAL code mathematically. And then in addition, when you create this business logic, it may not just create one TEAL contract, it may create multiple contracts. And it will do all that below you, and you don't have to worry about it. And then you can just use their deploy tool to deploy the smart contract. Hopefully, we're going to try to get you guys a Reach talk, where someone can come in and give you a talk on how to use the Reach tool. Just wanted to let you know it's available. And then the Python library kind of looks like this. I'm not going to go through this example, but here's some example Python for stateless smart contract. And so there's a bunch of and conditions checking different properties. And then when you run the PyTeal compiler on it, it actually produces that TEAL. And then obviously we have documentation for PyTeal. You can go out and take a look at that. This is all linked from our developer website, developer.algorand.org. And then Reach has a reach.sh site that has their whole framework laid out. And they also have documentation as well, and some tutorials that you can walk through if you want to learn how to use Reach. Okay, a couple last final things here. Make sure that we got a boilerplate for the approval program for stateful contracts out there. We got an example stateless smart contract out there, but adhere to these guidelines. I beg you to please look at that link and read through the guidelines that protect you. And then size limitations and opcode costs. That's just, most folks who are new to developing smart contracts don't understand there's limitations. So we want to make sure that you read over those. Okay, and then this presentation, the examples you saw in here, is available at this URL. I'm going to let you leave it here for just a second so you can take a screenshot if you want to. Make sure Russ is going to post the link to the presentation I just gave into the chat as well. All right, so make sure you take a look. If you were interested in getting those examples and setting it up yourself, it's fairly simple to do. And then remember to follow us on our Discord channel. Actually, I need to update that link. Go to the developer.algorand.org, and down at the very bottom, there's a link to our Discord channel. Use that link. Join our Discord channel. We have a lot of discussions. A lot of people help out there. So if you have questions, make sure you go there. And we have the developer portal. We also have forums if you want to use that. And then our GitHub link is there as well. And we do an office hours every 2 weeks for different things with Algorand. If you're interested, go to algorand.com/developers and sign up. So that's pretty much it. Russ, you want to give me some questions?
Yes, sir. Very engaged group here today.
Okay.
First one is, what are the main differences between TEAL and Solidity?
Okay. So Solidity, if you think about Solidity, written, it runs on a VM, and technically you can think of it somewhat like that with Algorand, but it's a Turing language. It has different function calls, and in Solidity you can actually instantiate a transaction. For us, that's not possible today. That may be possible in the future. We're making some significant improvements to the TEAL language to let you do some really cool stuff. But so ours is event driven. You drive smart contracts with transactions into the system. Whereas with Solidity, you can actually generate those things inside of Solidity, right? Some condition happens, you generate this transaction and it sends it off, right? So currently that's not possible with Algorand. And you can't, well, like in a stateful smart contract, you can't approve spending transactions currently, and that's likely to change as well. But those are the primary differences, and obviously. But I will tell you though, is with Algorand, everything is about speed. We have right now we have over 1,000 transactions per second capability. We're trying to drive that initially to 10,000, on our way to something like, I don't know, I think it was like over 40,000 transactions, 48,000, something like that, transactions per second. The only way we can do that is that we have to have strict guidelines around layer 1 smart contracts and what they can do. And that is all so the system continues to perform optimally. And you understand in Ethereum, you don't get transaction finality immediately. On Algorand, generally 4.5 seconds, you have transaction finality. Major advantage to Algorand. And obviously throughput is amazing. Our fees are next to nothing. There's fractions of a penny for a transaction.
Yeah, and that was one of the answers I gave for TEAL. Why TEAL and not a higher level language? And
yeah, well,
so basically performance is it, right? And
yeah,
we found the VMs.
Yeah, but we are working on layer 2 contracts that are written in Clarity, and which is a JavaScript-like language. And we'll also have we have folks already working on JavaScript to TEAL compilers, just like we have for PyTeal. So just so you know, those are in the works.
Okay. And this is another flavor, I think, of that same question we started with, but why is TEAL so severely limited compared to Solidity? When will Algorand have a Solidity-like ASC architecture?
Yeah, so stay tuned is what I would tell you. We have, like I said, we have some fairly sophisticated things going to be coming to TEAL over the next couple months, hopefully. Right now, though, understand that the reason why Algorand's process has always been, our number one focus is we got to keep speed. And in order to do that, there's some unique ways you can build applications that you probably wouldn't have to do, like you saw me doing the atomic groups. Probably wouldn't have to do that in something like Solidity. But in the same regard, you could wreck the chain with a piece of bad Solidity, right? That's not going to happen with Algorand. That speed is the most important thing to us, and making sure that it can work with most application types. So I would say we started with pretty tight constraints, and now we're opening those constraints up because we know we can get the throughput. So as those constraints open up, you'll see a lot of things change, like looping, for example. We'll most likely add that very soon.
And last two questions. Is there an IPFS equivalent for Algorand?
Yeah. So we get this question a lot. IPFS is distributed file system. We have examples on the developer website that show writing Algorand NFTs and storing the data in IPFS. For us, that's just another distributed file system that we can interact with. And we have some fields that you can use, and when you build an asset, that you can link over to the IPFS link. So you go to the developer, just go type IPFS into our search engine on our developer website, and you'll see.
Yeah, I posted one of the links of one of the solutions that Eric wrote on that. And then also, last question, I believe here, we can also open it up any verbal questions, but what are the best dev tools when coding in TEAL?
Okay, so
I know you mentioned a few of them.
Yeah, okay, well, Russ probably got the best layout of tools. There's some really, is it Algorand, the one that's really got the really tight, nice interface for, I would suggest you look at that one. I'd suggest you look at all of them. There's a bunch. Russ probably posted several of them. If you go to our community page on the developer site, there's a link for a bunch of different tools that you can use. All I did was use VS Code and a TEAL plugin for just giving my color coding. That's not necessarily the ideal for most people. There's other ways, other tools, much more capable tools out there today. I have this pattern, the way I've been doing things, and I'm kind of stuck in that way.
Yeah, I put the link in there, and there's actually a section on the community page just dedicated to smart contract utilities and libraries too.
Yep, cool.
All right, any other questions from anybody out there? All right, Jason.
Okay, well, Anthony, I don't know if you're still around there, but we really appreciate you letting us come on and talk to everyone. I hope it was beneficial to the participants.
Awesome. No, thank you all very much for joining. Jason, Russ, thank you so much for joining us this evening and for the presentation. That was deeply enjoyable, and I know that everyone found it very useful and yeah, awesome, really. For everyone who joined today, thank you very much. This was event 5. We have one in 2 weeks' time. And then we will announce also the programming for the second half of this education series. And for those of you that are looking to get stuck in building applications, we will be announcing details of the Encode Algorand Hackathon, which I suspect will happen towards late summer, probably August will be the start date for that. So continue using these sessions to learn, to build your skills base, to ask questions, to get involved and explore. And we hope to see you all kind of very soon in future events and hacking. Jason, awesome. Thank you very much for the talk today. And Russ, thank you for answering the questions so methodically. Great. Thanks, everyone. We'll get the slides and video up for this.
Thanks, Anthony.
And have a good evening, afternoon, morning, wherever you are. Thanks.